Assalamu alaikum. This is the section 5 and the last section on lecture 1 of the fundamental of soil science course. We are talking now about clay mineral, and as I told you that if you have a sheet of gypsite, octahedra, and a sheet of silica, you will obtain one mineral, and if there is a sheet of silica, gypsite and silica, this is called 2-1 mineral. All are 2-1 mineral, with exception these are 1-1 mineral, like this shape. This 1-1 mineral, and this is 2-1 mineral. So if we would like to know the formation of clay mineral from a basic building unit. I told you that the basic building unit of clay mineral is silica layer, gypsite layer, and porosite layer. Silica layer has a chemical composition of Si2O5 because it is considered as a phyllosilicate. Gypsite layer or dioctahedral layer it has a chemical structure of Al2OH6. Porosite has Mg3OH6. If you have a 1-1 mineral, 1-to-1 mineral, so you have a layer of silicate and a layer of gypsite. When this and this gain together, 2OH should be lost, and then its chemical structure should be Al2, Si2O5, OH4. This mineral called kaolinite. On the other hand, if there is a porosite layer, the structure would be Mg3 instead of Al2 because it is trioctahedral mineral. Mg3 Si2O5OH4. This is called a serpentine mineral. 2-to-1 mineral. In 2-to-1 minerals, there is a 2 silicate layer and 1 gypsite layer, and consequently 4 OH should be lost, and its chemical structure should be here Al2 Si4 O10 OH minus 4 OH2. This mineral called pyrophyllite. But here in trioctahedral, the mineral Mg3 instead of Al2, and the mineral called talc. The 2-1-1 mineral or 2-2 mineral have 4 layer, 2 of silicate and 1 gypsite layer and 1 porosite layer, and the porosite layer here gain to the structure of pyrophyllite without losing OH. So you have two type of chloride dioctahedral. It's a pyrophyllite with porosite layer addition. Here chloride trioctahedral, it's like talc mineral added with a layer of porosite layer. So it's summarizing. This table is very important table because it's summarizing how clay mineral formed from the basic building unit. So I want you to know that the building unit of clay mineral is silicate layer, gibbsite layer, and porosite layer. The type of mineral is 1-1 mineral, 2-1 mineral, 2-2 mineral, or 2-1-1 mineral. So you have kaolinite, Al2Si2O5OH4. You have serpentine, you have pyrophyllite, talc, chloride dioctahedra, and chloride trioctahedra. Actually, during crystallization from magma, sometimes there were a deficiency of silicon in magma or lava and the excess amount of aluminum. If this case occurred, then the tetrahedral space should be occupied by aluminum instead of silicon. If this happens, this process called isomorphous substitution. Isomorphous substitution is the replacement of one ion with another having a different charge, because aluminum have +3 while silicon have +4, with another ion having a different charge but with no charge in the mineral structure. Then is the replacement of one ion with another having a different charge does not change in the mineral structure, means that no change. It means that its size approximately equal to each other. The size of ion to be displaced should be equal to the size of the replaced original ion, or if there is a difference, should not be more than 15%, more or less than 5 to 15%. In case aluminum replace silicon, in clay mineral, the net negative charge will be increased by 1, and the mineral should be make the mineral should be absorb a cation to make equilibrium. The cation like sodium or potassium and so on the surface of mineral. So here is a tetrahedra, and if you have a deficiency of silicon, the aluminum replaced or the fold the empty space, because its volume is approximately equal to the silicon, with a difference not more than 15%. And if the isomorphous substitution occur, a negative charge will be obtained and should be equilibrium. Should a cation like potassium adsorb to the surface of the tetrahedra to make equilibrium. So if you have silicon, the silicon replaced by aluminum, and sodium can be absorbed to make equilibrium or exchange to the surface of the unit. Maybe sodium, if there is 2 aluminum replaced by 2 silicons, then calcium may be exchanged to the surface of the unit. In octahedra, you will do not found isomorphous substitution. In octahedra, remember, in octahedra, I told you that mostly aluminum, magnesium, and iron are formed in octahedra because the space here is larger. So you can found silicon here in octahedra, but you can found here aluminum +3, replaced by magnesium or iron, nickel, zinc, and copper. If these occur, then you have 3 negative charge and 2 negative positive charge. Here 3 positive charge. Here is 2 positive charge. Then an exchange of Na should be occur. Okay. These for isomorphous substitution. An example of isomorphous substitution is the first example is isomorphous substitution in octahedra. You will find here a mineral called montemorillonite. Here the pyrophyllite unit is Al2Si4O10OH2. But if there is the isomorphous substitution with Mg instead of Al, so you will find a negative charge and the Na exchanged to the surface of mineral. The Na sodium usually surrounded by water, absorb water, and this mineral called montemorillonite or cementite mineral because it absorb water and its size may increase in the presence of water because it may absorb 4 layer of water. As you know, the octahedra is on the middle, not on the surface. So the charge the charge on the surface will be low. Is this correct? Look here. It's mineral 2-1. The octahedra is surrounded by tetrahedra. So if you have an isomorphous substitution on tetrahedra, then you will have a high negative charge on the surface and can be absorbed potassium, for example. But if you have isomorphous substitution on the middle, so the charge will be lower. So the charge lower on octahedra, isomorphous substitution, than tetrahedra. Why? Because the octahedral sheet is on the middle and surrounded by 2 tetrahedra. So no potassium fixation due to low surface energy. The surface of the charge in the isomorphous substitution in inner octahedral layer, but have a high specific area because it's expanded. Look to vermiculite here. The isomorphous substitution is in tetrahedra, and tetrahedra is on the surface. Look here. If there is the isomorphous substitution in tetrahedra here, in tetrahedra, so the negative charge will be on the surface, and consequently, the negative charge will be more than in montemorillonite. Is this correct? Yes. Yes, correct. So if you look to the vermiculite, we have 2 types of vermiculite. We have vermiculite dioctahedral and vermiculite trioctahedral. In dioctahedral, the isomorphous substitution present in tetrahedra and in octahedral layer. Usually, maybe you found in tetrahedra and octahedra, or maybe you found only in tetrahedra. And try like here, only on tetrahedra here, not in octahedra. In trioctahedral vermiculite, the isomorphous substitution present only in tetrahedra. So the surface charge is larger than montemorillonite, 200 centimole per kilogram, and montemorillonite is 150, between 80 to 150 centimole, and here is between 150 to 200 centimole per kilogram.